Hello friends, dear students, I'm back once again, myself, Dr. Mansi this side. We have met many a times earlier discussing about different angles of chemistry, some point of time periodic properties, some point of time, galvanic cell, electrochemistry and all this thing. So this time I'm back here to discuss and deliver a few ideas about quantum numbers. So to understand quantum number, first we have to recollect Heisenberg's uncertainty principle. So what is Heisenberg's uncertainty principle? What he said and how he could say this? He said that electrons cannot only be considered as particle. Rather, it has some wave natures into it, from where wave-particle duality theory comes. Secondly, Heisenberg said that it is impossible to define or to describe electron in terms of both momentum and its position at a particular time. It is impossible to describe electron in terms of both its momentum and position with highest precision, with absolute precision, is not possible. It is impossible. So, electron can be described with probability when we are talking about its position and momentum. When we describe electron both in terms of position and momentum, we have to take the help of probability. It is a chance. And finally, he also said that atomic orbital is defined as a region in which at least there is a probability that 90% of the time electron can be found out. So atomic orbital is defined as a region in space in which the probability of finding the electron is greater than at least 90% or even more. So to understand atomic orbital, we have to understand the quantum theory. What is it? We all know quantum theory or the quantum theory based on quantum number comprises of 4 different quantum numbers. And these quantum numbers, what are their function? Ideally, they give you the exact location or the address of an electron in an atom. Where it is, what is its spin, how it is rotating, how many subshells or the degenerate orbitals will be there, and what would be the number of electron holding capacity in each subshell. All these things are given by or can be understood from the concept of quantum number. Now there are 4 quantum numbers and that give the exact location, as I said, or the address of the electron in an atom. They are principal quantum number represented by n, which defines the shell number. I mean to say K shell, L shell, M shell and so on. Then comes angular momentum quantum number or azimuthal quantum number, which is defined by the size and energy of the orbital and is represented by L. Then comes the magnetic quantum number represented by M, which defines the information about the number of orbitals in a subshell. How many orbitals will be there in a subshell and their orientation as well. And finally, the spin quantum number represented by S gives you the idea of the direction of the spin of the electron within an orbital. Now, moving into the deep detail of the principal quantum number as it is represented by n, we can say the larger the value of n, the farther the shell is from the nucleus. As the value of n increases, then the shell is becoming more distant from the nucleus and it has an integer value starting from 1. That is, the principal quantum number may have values 1, 2, 3, 4 and so on. As the value of the n increases, the energy gap between the successive shell decreases. So we can see from the picture, the first one, that is when n is 1, that is assigned as K shell. When n is 2, it is assigned L shell. When n is 3, it is assigned M shell. And when n is 4, it is defined as N shell and so on. So, as the number of n increases, the distance from the nucleus of the outermost shell increases automatically, and the energy gap between the successive shell decreases. Talking about azimuthal quantum number represented by L. Azimuthal quantum number starts from 0 and extends up to 0, 1, 2 and 3. That is, it is having a value n minus 1. Whatever the value of n would be, L would be less than 1 from n. Now, for example, when n is 2, L is 0, and when n is 4, L is 0, 1, 2 and 3. All these values will be included. When L equal to 1, we say the subshell to be S. When when L is 0, we call the subshell as S subshell. When L is 1, we call the subshell to be P subshell. When L is 2, it is D, and when L is 3, it is assigned to be F subshell. Now, this is the representation of the values of the quantum number, principal quantum number, and along with it, depending on the value of the principal quantum number, the variation of the azimuthal quantum number. What I said that azimuthal quantum number is simply represented by n minus 1, where n is the principal quantum number. And the value of the principal quantum number starts from 1 and extends up to 1, 2, 3, 4 and so on. So depending on the value of the principal quantum number n, the value of the azimuthal quantum number changes. And what are the corresponding subshells? Let us understand. When n equal to 1, that means the electron is in K shell. If n is equal to 1, naturally L will be n minus 1, that is 1 minus 1, that is 0. 0 means it is in S orbital. K shell, S orbital. When n equal to 2, that is L shell, we can say the value of L equals to 1. That means it will be 0 and 1. 0 represents 2s orbital and 1 represents 2p orbital. 2y because the value of n is 2. When n is 3, that is M shell. Naturally, the value of the azimuthal quantum number will extend up to 2, that is n minus 1. That means 3 minus 1, that comes to 2. So, it will range from 0, 1 and 2. 0 represents 3s orbital. L equal to 1 represents 3p orbital, and L equal to 2 represents 3d orbital. Why 3? 0 for S, 1 for P and 2 for D. And why 3? Because the value of n is 3. That is it. Hence, in the first shell where n equal to 1, L equal to 0, so the first shell of electron contains only S subshell or orbital. And in the third shell where n equal to 3, that is L equal to 0, 1 and 2. So the third shell will consist of SP and D subshell. Moving to magnetic quantum number, the value of magnetic quantum number is dependent on again azimuthal quantum number. The value of azimuthal quantum number depends on principal quantum number, and the value of magnetic quantum number depends on the value of the azimuthal quantum number. And the value of M is equal to plus minus L. That is, it extends from minus L to plus L and in between. Let us have an example for an S subshell. S subshell, what does it mean? L equal to 0. For L equal to 0, the subshell will be S. So when we consider S subshell, L will be 0. And so for M, that is M equal to 0. That means plus minus L, that is plus 0, 0 and minus 0. And it doesn't make any sense talking about plus 0, 0 and minus 0. All the values are the same. And in an S subshell, there will be only one orbital, as there is only one value for M. What I mean is, when we talk about L equal to 0, then azimuthal quantum number becomes 0. That means there will be no further subshell in S. S subshell, there will be only one orbital. And electron holding capacity in one orbital maximum is 2. So S can hold maximum up to 2 electrons. For example, P orbital or P subshell. For P, the value of L will be 1. N minus 1, that is 1. For P, it will be 2 minus 1. Here for P, L is equal to 2. So, M equal to 1, n minus 1, that is 0, minus 1, 0 and 1. So, in P subshell, there are 3 orbitals and the values are like this. For L equal to 0, it is S. For L equal to 1, it is P orbital having M values. Let us consider all this. As of now, whatever quantum numbers we have discussed, let us talk about this. L is the principal quantum number. When L equal to 0, then, L is the azimuthal quantum number. When L equal to 0, the magnetic quantum number M is also 0. That is S orbital. When L equal to 1, magnetic quantum number will be plus minus 1. That is minus 1, 0 and plus 1. That is Px, Py and Pz. Orbital orientation we are talking about. Now, L equal to 2, that means D, M equal to minus 2, minus 1, 0, plus 1 and plus 2. And finally L equal to 3, that is F orbital. M ranges from minus 3, minus 2, minus 1, 0, plus 1, plus 2 and plus 3. Now talking about these are the concept of the principal, azimuthal and magnetic quantum number. Now talking about the orbitals. Although subshells have different energies, but within a subshell, there are degenerate orbitals. I mean to say, S orbital has only one degenerate orbital. P can be broken into 3 degenerate orbitals. D can be broken into 5 degenerate orbitals. Why 5? Why 5? You see, for L equal to 2, M equal to minus 2, minus 1, 0, plus 1 and plus 2. That means there are 5 values. So it can be degenerated. D orbital can be having 5 degenerate orbitals. And lastly, for F orbital, it will be having 7 degenerate orbitals. So although the subshells may have, that means S and P and D and F, these are subshells, they may vary in their energies, but the orbitals within the subshell are having equivalent energies, are degenerate. They have equal energy. That is, 5 orbitals within a D subshell are all degenerate. Okay. Shell is the principal quantum number, KLMN. Subshell is the azimuthal quantum number, SPDF. Magnetic quantum number represents the orbitals, that is the degenerate orbitals. How many orbitals are within either S or P or D or F? And these orbitals within a subshell are all equal or equivalent in energies, so they are called degenerate orbitals. And each orbital can hold a maximum of 2 electrons, we know. Hence, an S subshell, as it has no orbital, no broken up orbital, only one, it will be comprising of 2 electrons. It can hold maximum 2 electrons. P subshell, made up of 3 orbitals, can hold 3 to the 6 electrons. Similarly, D subshell, made up of 5 orbitals, can hold a maximum of 10 electrons. And obviously, F subshell, which is made up of 7 degenerate orbitals, can have 7 to the 14 electrons. That's it. Talking about the spin quantum number, that is S. Talking about the spin quantum number, we have to first refer to Pauli's exclusion principle. What it says? It says that no electron in an atom can have all the 4 same set of quantum numbers. There are 4 quantum numbers. According to Pauli's exclusion principle, a particular electron in an atom never can have all the same values for the 4 quantum numbers. The Pauli's exclusion principle states that no 2 electron in an atom can have same set of quantum numbers. We consider a particular atom. We take two electrons which are in the same subshell and same orbital, even then they will not have all the four quantum numbers having the same values. At least if all the other three values are same, then they must have different rotation. That is, their spin quantum number must vary. I'm coming to it later, but before that, spin quantum number, what it says that if an orbital is holding two electrons, then the electron must be spinning in opposite direction. One in clockwise and the other one is in anti-clockwise. If M has two values, that is plus half and minus half, and if plus half represents clockwise, obviously minus half will represent anti-clockwise. This picture you can see M having plus half and minus half. One is having clockwise rotation and the other one is having anti-clockwise rotation. This table will give you the idea about the electron holding capacity of the orbitals and different elements present in periodic table. How many elements will be present in a particular row or column, that is also represented by this quantum number. Talking about NL, that is the principal quantum number, and azimuthal quantum number. If n equal to 1, obviously L will be n minus 1, that is 0. Magnetic quantum number M will also be 0. That means it will be having its electron in 1s orbital. 1s orbital. So maximum elements, in 1s orbital, the number of electron holding capacity is 2. So the elements will also be 2 in K shell. In talking about N, that is the principal quantum number when N equal to 2, L will be having two values, 0 and 1. That means L equal to N minus 1. That means 2 minus 1, that is 1. So it may have values 0 and 1. Then the magnetic quantum number will be minus 0, 0 and 1. And since N is equal to 2, the orbitals will be 2s and 2p. 2s for 0 and 2p for all the three things. And that means total number of electron holding capacity is for p orbital 3 2s are 6 and for s orbital 2. That means 6 plus 2, that is 8. So number of electron that L shell can hold equal to maximum number of electron is 8. For n equal to 3, that is principal quantum number, the value of principal quantum number is 3. Then the value of the azimuthal quantum number will be 0, 1 and 2. N minus 1 equals to 3 minus 1, that is 2. So it will be considering 0, 1 and 2. 0 for 3s orbital, minus 1, 0 and 1 for 3p orbital, and minus 2, minus 1, 0, 1 and 2 for m orbital. So in all, it can hold for s orbital maximum 2 electrons, for p orbital maximum of 6 electron, for m orbital maximum of 10 electron. In all, 18 electrons. And the shell in which it will be having all the electrons for n equal to 3, principal number equal to 3 is M shell. And this goes on like this. And that is all I had to say in today's lecture. Thank you so much for being patient and listening to me.